So, good afternoon. Welcome to Krishna's classroom. We begin with a new series of lectures entitled Inner Product Spaces. Now, this is in a way a continuation of the linear algebra lectures that we gave, but probably I would like to keep it as a separate unit. Usually it comes as a part of a linear algebra course. Now let us just recall something that we did earlier. We introduced the concept of a vector space over a field F, and we considered the finite dimensional cases, and we had the concept of addition and scalar multiplication, which we called it addition and scalar multiplication, essentially defining associating certain functions with those vectors. Pairs of vectors, or say mappings from x cross x to x, and say f cross x to x with certain properties, which are essentially inspired by what we have observed on R, R2, R3. But conspicuously, we have looked at only the qualitative properties of R, R2, R3, and just confining ourselves to the facility of addition and scalar multiplication. It is amazing that we could get a wonderful generalization of this. With a lot of power, we could define transformations on these spaces, and then we could look at the central problem of what is called matrix representations, and make a deep inroad into whatever is possible on this. In fact, we have tried to obtain what we call the most efficient representation of this. Wherever it is possible, we could get the diagonalization of the operators. That means introduce a suitable basis for the space in which the transformation that we are considering has a diagonal representation. And wherever that is not possible, and there were cases where it was not possible, we went for certain canonical representations which are simple enough for our operations. But conspicuously, we kept away from introducing what is called a dot product, or the analog of a dot product, or the analog of a length in these cases. Now I think it is time we introduced our experiences, or we expanded on our experience of working on R, R2 and R3, where we had the concept of length of a vector as well as the angle between two vectors, or the distance, and through the length we could also get the distance between two vectors, and which opened up a new structure. It's a very powerful structure that we introduced, and we can see that this properly gels with the linear space structure that we have on vector spaces, provided of course some restrictions are made on the choice of the the field, etc. And there are many situations where this whatever you see on R2, R3 gets generalized to give you some wonderful results. But this is what we are after now. Okay. So we begin with looking at R2 and R3. R we keep it in the on the sidelines because we can always go to that. In some sense it is trivial and even non-visible. But R2, R3 you have got a lot of geometric perception and it gives good insight into whatever is happening, and the sort of concepts that we want to introduce are naturally, seen there. So let us work on that. So look at R3. Also, let me start with R3. R3 is the set of all. It is actually the linear space structure attributed to R cross R. So you have a triple where each xi belongs to R, and of course for I equal to 1, 2, 3. And apart from that, so you look at the entire collection of these triples. And R2 will be, of course, an ordered pair x1, x2 with the xi belonging to R analogously. Now R3 is and we also know that it is of dimension and you know that the choice of the field is significant in deciding the linear space structure of the set R3. Okay. For instance, if you were to choose Q as the ordered basis, as a field, then you see that it is still a vector space over Q, but now the dimension becomes infinite. Okay, so this we have discussed earlier in our lectures on linear spaces. Okay, so that is significant. Now we have the usual addition. Addition is defined as we call or where x is equal to and we have the concept of scalar multiplication. The scalar multiplication is this. See, alpha times x is defined as that they are, once again, by definition, they are vectors. So the sum of two vectors is a vector, the scalar multiple of a vector is a vector, and all these have geometric significance. Okay. And then with respect to these two operations, it induces a structure called a linear space. So R3 is a vector space over R of dimension 3. These are the addition and scalar multiplication that we have done. Now what we are going to have is just to recall what all things we have. We have the notion of length. Which we have not considered earlier. That is, we have the length of a vector which is defined as what's the definition? And then we have also the concept of what is called a dot product. X dot y defined by which is related to the angle between the two vectors. So this corresponds to the length and angle is represented by the dot product. Now this is quite easy to see. What you have to do is, maybe I leave the computations to you, how this is related to the angle between two vectors. So let us take two vectors A then A is given by the triple A1, A2, A3. B is given by now a plane, we assume A is not equal to B. Now we will consider the case A equal to B later. Okay. Now there is an angle between these two vectors. Or we need not say that A is not equal to B. A equal to B is also taken care of in this analysis. Now you see that we want to measure the angle between A and B. So call this theta. Okay. Now how do we end up with relating it to the so-called dot product? Let us see this. Now you see that there is a unique plane determined by A and B. Now we can measure the angle between A and B in that plane. And you see that, how do you do that? Okay, let us compute this in terms of, our objective is to compute theta in terms of A1, A2, A3, B1, B2, B3 and find an expression for that. So what we do is we draw a line in the plane determined by A and B so that it is perpendicular to the line or the vector A. Okay, we have not said anything about what is orthogonal or dot product equal to 0. Such things we have not introduced at all. So you see that since we are working at a point, say this is A, let me write this A, this as B, and now let me say this is C. So you see that C is lambda times because it is along the same line, it's a scalar multiple of that, so lambda is a real number. Okay, it may be positive or negative depending on where the point C happens to be, but C is a unique point determined by taking the orthogonal from B to the line OA. Right. So it is given by lambda times A1, A2, A3. Now we have to determine, so determine B, determine lambda such that BC is perpendicular to OA. So what do you have? We know the Pythagoras theorem. What does the Pythagoras theorem say? That the length of OB, that is OB square by Pythagoras theorem, we have OB square equal to the length of OB square equal to where of course I have put O length of it. This is the Pythagoras theorem, OB square equal to this. But we know that OB square is equal to now OC square we don't know. Yeah, OC square is essentially lambda square into A1 square plus A2 square, A3 square. Now we compute this. What is BC square? BC square from vector algebra, we know that BC square, this is equal to see what is this vector? See if you compute this, you can easily see. Let's compute the value now. This let me call this D. Now you draw a line OD parallel to CB and complete the square. The rectangle. Then you see that BC square is essentially OD square, which is equal to, what is OD? OD is equal to, now D has coordinates. D has coordinates okay. B1 minus lambda A1 that is, this is essentially OB minus OC. So that's what we have written. Therefore, OD square this is equal to the sum of the squares of these terms, that is B1 minus Peetham square. Now, what you need is that once you get BC square, then you get OC square is equal to, okay, right. So BC square is equal to, is also equal to, another expression for this is that it's B1 square plus B2 square, B3 square minus lambda square so these two should be equal. Okay, this is from Pythagoras theorem. Okay, now compute this. If you compute this, then what happens? You see that okay, you equate these two. When you equate these two, you see that the two things cancel. Now this is equal to okay. Twice lambda, what is that? A1 B1 this is from the, so equate these two. If you equate these two, this is what you obtain. So what you obtain is this. They cancel. This and this cancels. And you end up with lambda square This is, and that means that and if lambda is not equal to 0, okay, if lambda equal to 0, okay, lambda is not equal to 0, then you have lambda that is lambda. Okay. Therefore, now we can compute this angle. This angle is in fact the cosine of this angle we can compute. So cosine of this angle OC divided by OB. And that you can compute from here. So OB is, this is equal to, what is OC? OC is, what we have computed is BC. Yeah. So BC okay, sorry, this is OC square. So OC we have already computed. So this is equal to square root of take OC I am just computing the magnitude of cos theta. So magnitude of cos theta is going to be this is the positive square root of this, and this you can now substitute lambda. Okay. So lambda is equal to, therefore this is equal to lambda square into divided by what you have, lambda is sigma ai square. So this is Okay. So this gives you okay. So that, of course, once you choose AI, BI, then the properly, then the sign will be taken care of by this. Okay, right. So you have got essentially sigma AI BI. So cos theta equal to I have not used the dot product at all in this calculation. I have simply used certain knowledge that we have from vectors about the length of vectors and just computed the cosine of the angle between these two vectors in this through this formula. And that is so there is no question of orthogonality used or any such thing used except in the form of what is called the use of Pythagoras Theorem, which is readily available to us. And so I think I'm not doing a cyclic process or anything like that in these computations. Okay, so this is what you have. Therefore, cos theta is okay. Now what we can do is we will introduce certain notations. Let us introduce we write A dot B then you have A dot A and B dot B bi square, and I can also introduce the following notation, that is, let me write A dot A, that is norm of A square, and use this notation throughout. So what you have cos theta equal to A dot B divided by so this is the formula that you get. I mean, this is essentially the angle between the vectors. See, this is what you have. and lambda times A is essentially the projection of OB on the line generated by OA. Okay, so this is what you have used essentially. So we had this this and then we computed cosine of this. The cosine of this is actually OC divided by O. That's what we have. Okay. So cos theta is equal to OC by O. This is what we have computed. And therefore, you get a formula for this. So the dot product that we have introduced is essentially the angle between two vectors. Okay. Now you can run the same program in the case of say R2. So for R2 there is a shortcut that you can easily use. For R2 you see that suppose you take R2. Okay, so in the case of R2, suppose you take two unit vectors. These are unit vectors. Okay, so this is of length 1, is also of length 1. Now, this angle, this is O, A, B, both are unit vectors, and this angle is say theta 1, this angle is theta. So the angle between OA and OB is theta 1 minus theta 2. So let us compute this. Cos plus theta. Well, we take theta equal to, then cos theta is, what is this? Now this we can work out. What is cos theta 2? Cos theta 2 is, suppose this is actually A1, cos theta 2 is B1, so this is B1, this is cos theta 1 is A1 plus sin theta 1 is essentially this one, so that is equal to B2 A2. Okay, we are assuming that length of OB now it is quite easy to see in the general case. Suppose OB is not equal to 1, the length of OB is not equal to 1, length of OA is not equal to 1. You can define vectors not necessarily equal to 1. In that case, what happens? You can define OA prime to be OA divided by length of OA in that case we also know what they are. So OA, OB, so this is equal to what is the coordinates of A prime, coordinates of B prime in that case are, see, the coordinates of A divided by the length of OA and the coordinates of B divided by length of OB, and then you compute it. So you get, in general, this is equal to, so the general expression is going to be again cos theta Okay, so that's in the case of R2. In the case of R3, you can actually compute this way. Therefore, you see that it is intimately connected with the angle between two vectors in the case of R2 and R3. Now, in the case of R, what happens? In the case of R, there are only two possibilities. In the case of, take R, so then you see that suppose you have a vector here and another vector B here. Suppose both A and B are on the positive side of the real line, then you see that the angle between them is 0. If one of them is on the positive side and the other one is in the negative side, then the angle between them is going to be pi. Okay, so you can easily work it out now. You can verify the formula for this case. So you have only two angles possible, that is cos 0 and cos pi. So you can easily see that the same formula works. So this is a general formula that you have, which I have designated using this notation. Okay. See, the problem with the directly measuring out theta is this. What is theta actually? You take the unit circle in R. Okay. So this is the radius is 1, and then theta is essentially the measure of the length of this arc. That is the arc. Okay, it is the length of the measure of this arc. And when we work out cos theta, that happens the length of a line segment. Okay, so we often express it in terms of the length of a line segment rather than the length of an arc. So these are some of the advantages that you have. That's why we have chosen to represent cos theta. But when you generalize it, quite often this concept of angle, etc., will be something very abstractly that we talk about, because we cannot, suppose you take an n-dimensional vector space and there is nothing like a concept of the angle between them, except in inverted commas we call something the angle. We can write cos theta again through the dot product, etc. So we can generalize this concept nevertheless. Now we observe the following. So we have introduced a certain notations already. These are the notations. We have defined the dot product in this way, and then the length, the square of the length is given by these two, and this we have designated by what is called, this is called the norm. Square. Square of the norm of A, that is the length of A. So this is essentially what is called, so this designates, that is okay, so that gives justification for calling it a angle. Okay, now we start from here and introduce the what is called the dot product. So the dot product essentially helps you to define the angle between two vectors as well as its length. So that's a new structure that we are introducing, from which you can get also the length of two vectors. Length of a vector. So let us look at this. What are the properties of this? So on R3 or R2, we consider R2 also R. Okay. So on R3, define the dot product or inner product of two vectors. X and Y by and we shall introduce a new notation. So this is the standard notation that we will be using throughout in this lecture. Now from this we also have norm of x square or in other words it is x dot x, okay, and which is in this case, see this is sigma x1 y1 plus x2 y2 plus x3 y3, that is summation of these terms, or sigma xi yi, and norm x square is equal to sigma xi square, which is corresponds to the length of the vector. So this measures the cosine of the angle So this is what you have, cos theta this is the cosine of the angle between, where theta is the angle between x and now you see, when this theta is equal to 0, okay, and suppose x is equal to y. If x is equal to y, then theta is equal to 0, and then you get see, inner product of x with y is equal to, so when zero, but the x may not be equal to we have by which you mean that then x is a scalar multiple of y, that is x is a scalar multiple of but if x is equal to y, then xy equal to these are some of the things that you can immediately verify. Now with the objective of generalizing this, so what exactly is an inner product? We shall make the following observations. Okay, we will just work it out. What exactly is it? So first of all, we observe the following. On R3, the inner product is associated with a pair of vectors. Therefore, what you have is this. And what is it? And this is a scalar. And this same statement holds on R2 or on R. Real number. Therefore, what is it? So the inner product is maps an ordered pair to xy, which is an element of R. So it's a map from R cross R R3 cross inner product is a map from R3 cross R3 to R. Okay, what kind of map is it? What are the properties of this? One of the things that you observe is that symmetry xy equal to yx. Now you see that the second thing is it is bilinear. Bilinear in the sense that it is linear in the first variable, also it is linear in the second variable. That is, you have these are not components. X plus z. Cx, y, so also that means this map is linear in the first variable, keeping the other one fixed, and linear in the second variable, keeping the first variable fixed. Okay. Now the next property, that is the following. That is further x, lambda x so one can also deduce that x lambda y these properties are true. Now you also observe that moreover is greater than or equal to 0 and equal to 0 if and only if. Now this is quite easy to do. Okay. So these are some of the vital properties that you can immediately verify for the inner product or the dot product. Okay. So these are quite significant, and you see, as is the case when you generalize this. Now we have observed what our dot product is all about when we decided to call it an inner product, and then you see that we are looking at the basic properties of that to understand what it is, and you see that it is associated with a pair of vectors. It's always associated with a pair of vectors, and the pair of vectors is mapped onto a real number. And what are the properties of this map? The properties of this map is that, first of all, it is symmetric in the sense that the image of xy, the ordered pair xy, is the same as the image of the ordered pair yx under this map. It is bilinear in the sense that it is linear in the first variable, keeping the other fixed. It is linear in the second variable, keeping the other fixed. And in fact, when you scalar multiply a vector, so this is lambda xy is equal to lambda of xy, and lambda x lambda y equal to lambda xy. Moreover, the inner product of x with x is non-negative and is 0 if and only if x is equal to 0. So these are the basic properties that the inner product has. Whether you have, now you see the three things that we look at is the usual inner product on R is the following. Xy. Inner product on the usual inner product of for x equal to and on R3 therefore on Rn, so in general, for any positive integer n over R, you know it is a vector space of dimension n. This is for n, and consequently that's a very natural way in which you generalize this. You can easily check that this definition essentially satisfies all these properties. Therefore, we somehow take this as the standard properties that defines a what you want to call an inner product. This is, I am talking about the usual inner product. Okay. I want to make some remarks on this. We look at this, the following vector space. Now you see that we have some complex, okay, make some remarks about this. We have said in the beginning that when we are taking up the study of inner product spaces, we are going to have some restrictions on the choice of the field. Okay, so we choose for vector spaces with the choice of field the associate as either that's a restriction that we want, and we know that we have the concept of vector spaces over the field C. I mean, in fact, for some reason or other, we prefer working on the field C, because you see that you will see, as we have seen earlier, that if you are working on a field which is algebraically closed, that means all polynomials over that field has roots, all the roots in the field itself. Now this property is satisfied by C, but it is not satisfied by I. As you have seen, the polynomial x square plus 1 equal to 0 has no roots in R. Okay? Whereas it has all its roots in C. In fact, C has the property that, in fact, the whole process of extension from the real field to the complex field has been motivated by the requirement that you should have all polynomial equations to have roots in the field itself. Okay, so it's an algebraically closed field. So it's nice to work with C. Therefore, C is very natural in our formulations. I think I will stop here. I will start with comments on this and then go to consider what is called C3 over, or more generally, Cn over C, where n is equal to 1, 2, 3, etc. And in that case, you see that there are some natural modifications that you have to introduce for the inner product, and we will discuss that. And we do it in such a way that when we restrict to real fields, okay, the new definition that we are introducing, or the new set of properties that we suitable properties that we demand for the inner product will coincide with whatever we have done on the real case. So with this, let me wind up this lecture. Now I will start with considering what is called Cn over C in my next lecture. Thank you very much.